Let's go through the plan for this week really quick. We have quiz 3 on Wednesday. It's showing nothing on the monitor, no signal. So it's an OR logic. Either this one works, either these ones work. So what's going to be covered on the quiz will be the dials, terminal characteristics, and BJTs, NPN. It will be a very classic problem. Won't be very difficult. Just trying to test you if you can remember all these fundamental equations. Closed book, closed notes, but you can use a calculator. You can even use your touchpad or a phone if you wanna. If you have an app, better calculator as an app on your phone, which is fine. You can use it. But just cannot Google for something else, and cannot look at your notes. So what's going to be covered on the midterm? DAC, ADC, the diagrams, but not the NLs, DNLs, but diagrams, and all the states, right? So that one. And DACs, how to calculate the voltage from the Thevenin's equivalent and superposition, the series. It's hot. Diode. I'm going to cover here. NPN, PNPs. NPNs. And concepts. So I'm going to ask you to explain all these concepts. What are these? Can be CLM, latch up. If you cannot find enough notes from my lectures, you can still Google it and try to memorize or understand what are these concepts. So I'm going to ask you to explain these concepts in the exam. And using diagrams to help with interpreting all these concepts if necessary. So draw some figures and explain what's happening, right? Just think about yourself as a teacher. You are teaching someone to understand what are these concepts. And pin junction depletion region. Body effect. And IS, ID, and which one is larger, which one is smaller, and the reverse bias or forward bias. And the N-well resistor, sheet resistance, Y it is a constant, and Ni, Nn, Np, Pn, Pp, Na, Nd. Right. So totally 6 problems. 6 problems, 100 points. Any questions? No? Okay. So in the homework assignment for homework 3, if the problem is asking to draw the load line, it's actually pretty simple. Just draw a coordinate and do this. So the current here, so this is IC, this is VCE for the NPN transistor. And this is, so this point is called IC max, or in some of the textbooks you probably will see IC set, right? Or IC max. And this point is called VCE cutoff. And you can find the Q point somewhere and just label it. That's a Q point. And here is ICQ. Here's a VCEQ. That's where the NPN junction is being biased. So you can bias this NPN junction at any DC Q point, right? Anywhere, depends on how you bias it. But that's a theoretical maximum IC, and that's a theoretical maximum VCE, but that just won't happen. It's just theoretical values. Why? Because if you are looking at this example here, for example, I just biased these 2 points at 1 VCC. So now you understand why it's called VCC. Sometimes in CMOS it's called VDD. I forgot who asked this last year, probably Taylor. Why sometimes VCC, sometimes VDD, right? You will never see VDD in NPN junctions. This is a collector, right? It says collector voltage. That's why it's called VCC. And for NMOS, that's the drain. So all these top rails are called VDD because it's a CMOS logic. Here's a collector logic. It's a BJT logic. So it's called VCC. If I bias the base and also the collector at VCC, just using the same voltage source to bias it, and is that possible to have a VCE to be 0 to calculate for IC sat? Is that possible to have a VCE to be 0 at all? Just VCE 0, so I can calculate for IC sat. If you look at this curve, when IC sat is being achieved, VCE is definitely 0, right? That won't happen. Because VCE can never be 0. The PN junction has internal resistance. It's going to drop a voltage across it. So it will never be 0. But when we assume VCE to be 0, we can calculate for ICE. That's a theoretical maximum IC possibly can flow through this channel. But that won't happen. It's just helping you to draw the load line. Got a point here, got a point here. So whenever this point is being achieved, IC is 0. So you can get this value. That's the largest voltage drop across VCE. Will that happen? Possibly. If you totally turn it off, IC can be 0. If you turn it off, there won't be any ICs. There probably will be some leakage current flows through the flows through here, the junction. But whenever IC is 0, VCE is what? When there's no current flows through the circuit, no voltage drop across RC, so VCC here, VCC here. So this value is actually VCC, right? Theoretically, that's VCC. That's how I calculate these two values. Pretty simple, very simple. If I'm asking you to draw the load line, just draw a coordinate and calculate for IC set when VCE is 0. So what is IC set? Or IC max? What is it? What is this value? When VCE is 0, what is IC? Simply VCC over RC. And VCE cutoff, it's not open, it's totally off for the transistor. So no current and no voltage drop. VCC, VCC. Right, very simple. Just draw the coordinate and draw the load line, find the Q point, and just label it. So for the example I gave to you on Friday, so what's being asked over there is determine the Q point and find the maximum I think it's redundant, but maximum peak value of the base current for linear operation. Assume beta equals to 200. And here's the circuit. So it's called VBB. This is RB, which is 47K. And this is RC, which is 330. And that's VCC, which is 20 volts. So remember that if you have a VBB, if this voltage source is given, and this voltage source is given, the NPN junction, the NPN transistor here is already biased at a certain Q point. Okay, because you can calculate it. Why? Because VBE, of course it varies, but here we just ignore it because it's going to vary between 0.5 to 0.7, tiny, so negligible. And we just assume VBE to be 0.7 volts, and you have a 10 volts here, so minus VBE, because there's no VE here, this is directly shorted to the ground. So voltage drop here is 0.7 volts, and the total voltage drop is 10 volts, so you can definitely calculate for IB. IB is VBB minus 0.7 over RB, right? So you can find out IB because beta is given, so you can calculate for IC, which is beta times IB. So that's the Q point, because the circuit has been biased at this point. So if you draw the load line, I know I have an IC set which won't happen, but it's a theoretical value here. And I know I have a VC cutoff. Definitely, I can calculate for that. But however, right now the circuit is being biased at IC, and if you calculate it, I think this is somewhere around 39.6 milliamps. And I have to calculate for this guy first. What is this value here? How to calculate it? So this value is calculated when VCE is 0. So when here is 0, so the entire VCC will be dropped across this RC. It's going to be VCC minus 0 over RC, which is 20 volts over 330. I think this is 60.6 milliamps. So this point here is 60.6 milliamps, but now this NPN is being biased at a different IC, which is here, right? So this point here is 39.6 milliamps. So this is 60.6 milliamps, and now it's being biased at this value. So you can tell this is larger than 50% of this guy. Ideally, it should be 50%. Normally, that's how we bias the NPN transistor, because we can have a largest swing. But this will not give you a largest swing because it's going to be clipped at some point. Right? Because you cannot have a largest swing. So when IC is being amplified, you're getting this. If it's being amplified to a larger gain, it's going to be clipped on the top. So I have to find out the maximum peak current for IB, right? This is IC, so the y-axis is IC, and the maximum swing will be this, or the magnitude will be here. So that is called, or you can just say the Q point is closer to the IC set compared to the IC compared to 0. So here will be the largest swing for IC. That making sense? So you compare these two regions here and here. Which one is smaller? This is smaller, right? So that will be the maximum swing. Because for a sine wave, you know, if it's swing around this line, this Q point, right? If it's larger here, then whatever on the top will be clipped. So you have to find out use a smaller margin here as a swing, as a maximum swing for IC. So IC set minus ICQ. ICQ is this guy here. ICQ is 60.6 milliamps minus 39.6 milliamps, which is 21 milliamp, which is the maximum swing for IC. Then you calculate IB using beta, so you can answer the question. The peak value of the base current, because this is amplified current, which is IC. So the base current is over here, right? So the maximum right, to say the peak value of the base for linear is case is this one, right? 21 milliamps over 200, which is a beta. So just calculate for this value, right? So what is that? Calculate it. That's the IB peak, which is 105 microamps. Any questions on this? If it just asks you to find out the Q point, it's pretty simple, right? Because everything has been biased. Just use this voltage minus VB, you get IB, and IB times beta, you get IC. And the Q point is just the VCE, all the DC values for this NPN, right? VCE, IB, IC, all these values. Actually, if you know one of them, you can calculate for all the other ones. But whenever it's asking to get a Q point, you just want to calculate all of these values. IB, IC, VCE, right? Just calculate it so you know where it is being biased. You know, you get all these curves, right? So it's being biased over here. There's a different configuration which has a little RE being shorted to the emitter terminal. Another example. Determine the Q point values of IC and the VCE. Find IC set or VCE cutoff. And construct the load line. Just draw the load line. Or DC load line. And plot the Q point. Or just label the Q point on the load line. VCC is 20 volts. RB is pretty big, 2.7 mega ohms. And RE is 3.3K. So here's the only difference. You got a little RE here. So what's the application for all these NPN transistors when we are having a DC bias? It's being ready for what? We just don't have time to run all these AC examples for NPNs and CMOS in digital class. But in advanced, if you are going to graduate school for advanced analog design, you probably will learn a lot of amplifier design. So you are going to do a lot of AC analysis, but now it's just purely DC. We just bias the transistor at some point to make it ready for an amplifier. Right? So the purpose is to bias this at some point, and so we can swing the signal in the linear region. So that's the final purpose, to make amplifiers. But now we are not doing that. Just calculate for DC, the DC domain. Can we assume VBE to be 0.7 volts? Yeah, since I didn't mention IS at all. So VB is always 0.7 volts for examples like this. But can you calculate for all the IC and VCs just using VB and VCC? Let's just list the equations and see how that works. So definitely there's the IB here, right? IB equals to what? VCC minus VBE minus VRE. Here's a VRE. VCC, that's the total voltage drop, minus VBE minus VRE will be the voltage drop across RB, right? And because RB is given, so we can directly divide this thing by RB to find out our IB, which is 20 volts minus 0.7 minus VRE, which is unknown, 2.7 megaohms. How do we find out VRE? VRE is IE times RE, right? What is IE? IE is 1 plus beta IB. Beta is given. Is it given? Beta is 100. So only IB is a variable here. So calculate for IB. Just do the calculation. IB is 6.37 microamps. See, if you know IB, you can know everything, pretty much everything for the DC, for the Q point, right? Because beta is given. If you know IB, you got IC. If you know IB and IC, you got IE. If all the currents are given, for DC circuits, if you know the currents, you know everything, right? All right, that's IB. Because it's asking you what is the value for IC and VCE. So let's calculate for IC, which is beta times IB, which is 100 times 6.37 microamps, which is 637 microamps. And what about VCE? So if you know IC, you know IE. IE is 1 plus beta IB, which is 101 times this, and which is slightly larger than IC, 643.37 microamps. So if IE is already calculated, you can definitely find out VE, and you know VE, you know VRC. So VC just VCC minus these two voltage drops across these two resistors. Right, these are totally 3 drops, 1, 2, 3. If you know these two currents, it's pretty simple to calculate for VCE. VCC minus IC times RC minus IE times RE, which is 11.52 volts. So these two questions are answered already. And now find out IC set and VCE cutoff. What is IC set? So just one comment here. Assume IC equals to IE to find IC set. Just for this one. But in general, they are pretty close, right? Because the beta is high. It's for calculation. Since IC set is not a real value, right? So it doesn't matter. It's 2 or 3 micrograms variation. So now let's calculate for IC set. How to do that? So keep in mind, when you are calculating for IC set, you assume VCE to be 0. That's how to calculate it. It's pretty simple, right? When VCE is 0 volts, IC set or IC max, you probably will see IC max in your homework assignment, equals to VCC minus 0, that's VCE is 0 volts. So get the current, that's why I assume IC equals to IE for this case, because I'm assuming there's just one current flow through the NPN junctions from top to bottom, just one current when VCE is 0, because I'm going to use this voltage divided by RC plus RE, 20 volts over 10K plus 3.3K. So this is 1.5 milliamps. Then VCE cutoff is when IC is 0. When IC is 0, no current. So all the VCC will be dropped. There's no current, no voltage drop across the resistors. So the VCC will be dropped across VCE, which is 20 volts. Oh my God, this is so simple. VCE, IC. Just draw the load line. I'm going to ask you to draw the load line. Very simple. Just draw a coordinate, boom, a line. And label IC set. Just put the value here, equals to what, right? And VCE cutoff, what is the value here? And what's the Q point? Here's the Q point. That's how it's being biased. That's ICQ. That's VCEQ, right? Just label it. So you will find out where this guy is being biased. If you see that IC set is 1.5 milliamps and ICQ is 637 microamps, right? So that's the Q point, and this guy is 637 microamps, and VCEQ is 11.52 volts, and this VCE cutoff is 20 volts, that's VCC. So you can see that this guy is being biased a little bit over 50% or below 50% of IC set. Below, right? Because this is less than 50% of this guy. So when you are drawing this, you don't want to draw it like this. You want to draw it like this, probably, right? That making sense? You may see some problems like this. Determine whether the transistor is biased in cutoff, saturation, or linear region. So I'm going to give you a lot of several values for the R's, combination of the R's. For example, RB is 75K and RC is 1K. So it's a very classic configuration of the circuit. VCC is 12 volts. That's RB, that's RC. Where to start with for this type of problem? 75K for this guy, and 1K for this guy. And this is given. Since you know it's gonna, the IV curve looks like this, right? And that's a load line, and you have an IC set for this NPN. When VCE is 0, so which means the maximum current can possibly flow from top to bottom will be when VCE is 0 or something else. 0. So calculate for IC set first. It's going to be VCC minus 0 over RC, which is 12 volts over 1K, which is 12 milliamps. That's the maximum, no matter what. That depends on the voltage source and the resistor here already set up. That's the maximum you can get. Okay? And then you assume this guy is being operated in the linear region to find out IB, and use IB times beta, see what the current is flowing through IC. If it's even larger than this, that won't happen. So it's not being operated in the linear region, it's going to be saturation region. Right? That making sense? You're asking why it's not in the cutoff region. Because 12 volts is way higher than 0.7 volts. You know, before it's being turned on, there's no current. The 12 volts will be totally dropped across this guy. I mean, just at a very short moment. So it's going to turn on this turn on this PN junction. The PN junction at the bottom is NPN, so the PN junction will be turned on. The current is going to flow through RB, so the 12 volts will be dropped to a small value, to somewhere very close to 0.7 volts, right? So it won't operate in the cutoff region. So if it's not in the linear region, it's going to be in the saturation region. It's going to be here. Here's linear, here's saturation. If it's not in the linear, it's going to be in the saturation region. So let's look at this example. 12 volts, RB is this. So I'm going to calculate IB, which is 12 volts minus 0.7 volts over RB, which is 11.3 volts over this, 75K. What is this? It's like 0.15 milliamp. Can you draw a conclusion now? Wait, that's IB. As IB, this is too large. Because this guy times 100. So IC will be beta times IB, which will be 15 milliamps, which is larger than IC set. So impossible, right? So it operates in the saturation region. That making sense? Any questions? We'll move forward. You haven't realized we are done with BJTs. For lab tomorrow, we are going to use a stick diagram. Sticks. Is lollipops only where you use lolly in American English? Because Australian English use lolly for candies, right? You know that? And they use a biscuit for cookies. As a senior Chinese, I think my mom pretty much take zero sugar every year. She will never take, like, just grab a candy and eat a candy or lollipop like that, or chocolate across the year. But for Americans, sugar every day, right? And I had so during the autumn festival, it's a traditional Chinese holiday. I mean, we eat the moon cakes. Have you ever heard about that? It's a really sweet cookie for Chinese. And we gave a couple, like 4 moon cakes to our friends here. And she doesn't like it because she said it's not sweet at all. And we already think that's super sweet already. But she feels like it's not sweet at all.
What's the traditional sweet?
There's sugar cane. Yeah.
That's what's used for sugar.
Yeah, yeah. And I think the cookies here you can buy in city market, in the grocery store, is already saturated for sugar. If you just taste the sugar, you can buy the sugar cane, the bag of sugar from the grocery store. If it just takes the sugar, it's less sweet than the cookies. I don't know how that was made. What you think? I mean, if you buy some of the cookies or cakes in, yeah. Okay. You want to eat less sugar? I mean, I don't know. It's hard. You can get addicted to sugar already. It's hard to change your. But some of the Cokes they labeled as they use real sugars, real cane sugars in there. Right. Okay, let's get back to the topic. So for the, so remember last time I mentioned that Pmos are being used to pull the output to the power, right? And Nmos pull V out to the ground. So that's why for a NAND gate, two inputs, one output. What are these? None. So if you are using a circuit to implement this logic, these outputs should be implemented by the Pmoses. These are the ones. You need the Pmoses to make this work. And you need the Nmoses to make this work, right? So if you think about the circuit, you want to construct a Pmos circuit to make this happen. If I have to look at the input. So 0, 0, so both of the Pmos are on, it's being put to the VDD, and or one of the input is on, no, one of the Pmos is on, it is able to be put to VDD as well. Right, so it has to be parallel Pmos. Because it can be both of the Pmoses are on, or at least one of the Pmoses is on, and you can pull it to the VDD. You get a 1. So you can think about that. It has to be this, just two Pmoses in parallel, because either one is on, it's going to pull this output to VDD, right? And for this one, both of the inputs have to be on. Both of the Nmoses have to be on in order to pull the output to ground. And we only use Nmoses to pull the output to ground. It has to be Nmoses, and they have to be both on, so it's in series. That's how I constructed this CMOS level circuit for the NAND gate. Give some examples and directly get to the examples you're going to use for tomorrow's lab. So I'm going to use this is a Pmos. So for stick diagrams, I'm going to use this symbol. So these are the 2P plus, the 2P plus terminals, these two terminals. And here's a channel, and here's a gate. And for Nmos, two circles for the N plus, here's the channel, here's the gate. If you have different colors or markers, you can use it, which will be really nice. But if you don't have it, which is fine for the circuits, the complexity of the circuits we're going to use in the labs, it is fine just to use one color. Not a big deal, as long as you understand what's going on. Stick diagrams is really important. I mean, it's really handy when you are having a mid-level complexity for the layouts. So if you have a circuit like this, how do you lay it out? How to design the stick diagrams first, right? It has to be Nmos like this. So here's the Nmos, and get another Nmos, and one more Nmos, and just make the connections. Just short it together. We can simplify this, definitely. You can merge these two terminals into one, right? So what you're getting is this. So when you are drawing the stick diagrams, just feel free just to do whatever I just did over here. So how many gates determines how many transistors you have. Because you can control the gate and control the on and off for the transistor. Remember, whenever you are not really sure how many gates you have, how many transistors you have, just count for how many gates you have in there. Can this be amplified even further if you're not using these terminals at all? So the answer is yes, you can directly do this. Boom, boom, boom. Because this is just a metal node. It's nothing else, it's just a metal. So when you are designing the layout in electric VLSI, you can also do the same thing. So remember, if you grab a device from the library on the left-hand side, right, you're getting this, right? So here's a gate, and you got a channel, but there are no vias on the two sides, right? So you can directly just grab one, and you do not have to have a via, but only have two vias on the two sides. And so for the NAND gate, when you are drawing the stick diagram, you have two Pmos on the top in parallel. So two Pmos. I'm going to do this, 1, 2, and two Nmos, 1, 2, and the two Pmos on top are in parallel, right? So here are the two metal one lines connect to the power, that's VDD, that's ground. And these two lines will be merged here at one point. So these two Pmoses are in parallel and merged at one point, and then reach here, and these two Nmoses are in series. So I'm going to draw the line like this. And that's A. And because I have to have a via, convert it to the metal one layer and extend it to here. So that's a NAND gate. When you're designing stick diagrams, this is really fundamental structure, which is a NAND gate. For more complicated circuits, we're running out of time. So what about that? Just pay attention to tomorrow's lab. Probably I'm going to give you a 10 to 15 minutes lecture in the beginning of the lab. If you're not coming to the lab, which is fine, I'm going to upload the video probably in 30 minutes after the first session in the morning. Just keep in mind, refresh the browser and find out the video if you have some questions regarding the stick diagrams of the lab. And that's a 2-week lab, right? Any questions? No? All right, see you tomorrow.